Who would have thought that we'll be here for the last lecture of the short course? On Sunday or Monday, it just felt like such a long trip, right? I was thinking about what are all the things I'll teach, and it was just very overwhelming. But slowly and slowly, one by one, I think we've crossed several bridges, and we are here to finish up our short course. I want to summarize everything that we've done in our short course, all the key ideas that I have taught, that I hope will stay with you and may benefit you in the future, right? So what have we done in this class, in this short course? I think the two themes, the two keywords that have come up again and again are lithium ion cells and heat transfer. First of all, in my last 10 or 15 years, 10 years or so, I have integrated the two. I have studied heat transfer in lithium ion cells. You don't have to do that. You could, in your careers, study heat transfer in something else. Or you could study something else of lithium ion cells. Okay? So please be open to ideas. I have ignited a spark, I hope, in you all, and I hope that that opens you up to new ideas, not necessarily exactly what I taught, but maybe something else, some other ideas that come in your mind as a result of having sat here and thought about this for one intense week, and hopefully that helps you out in your future growth. Okay. Today, in the next hour or so, what I would like to do is to summarize the key things that we have learned in our class. We started. Let's make a list. We looked at fundamentals of heat transfer. We have looked at thermal challenges in batteries. We have talked about heat transfer theory, the mathematics of it. Yeah. We have talked about experimental measurements. In particular, we've spent a lot of time thinking about thermal runaway as a serious problem, both from a practical point of view and also from a theoretical point of view. How do we predict thermal runaway in a system? One thing that I would like to say there is that we have focused in our lab, and all of the teaching that I did was focused primarily on thermal runaway in lithium ion cells. But that is not necessarily the only system in which thermal runaway occurs. There could be other systems in which there is a positive feedback loop that causes thermal instability, right? All you need is a positive connection between heat generation and temperature rise. Heat generation causes temperature rise. Is there a mechanism in the system you're thinking about in which temperature rise causes an increase in heat generation? If that happens, that is going to lead the system to thermal runaway. Okay? In the case of lithium ion batteries, this connection is because of chemical kinetics. Chemical kinetics tells us that reactions happen faster and therefore generate more heat at higher temperatures. There are other systems. I briefly talked about a resistor, a simple example of a resistor. In a resistor, heat generation causes temperature rise, but temperature rise in turn causes an increase in the resistance, which could cause an increase in the I square R heating that happens, right? So even a simple resistor is subject to thermal runaway. It does not undergo thermal runaway in most cases because it is, the increase in resistance with temperature is so small that it is usually a minor effect. But if you look around, I encourage you to think about what other systems, engineering systems, may have this thermal runaway problem. If you can identify a system in which this happens, then I'm confident that the tools that we have developed for thermal runaway in batteries will be easily translatable to other systems in which thermal runaway may occur. Okay, so I want you to keep your minds open about other possibilities, not just lithium-ion batteries. Also, especially to those of you who were not coming into this class familiar with heat transfer, I hope I have introduced you to some fundamentals of heat transfer. Heat transfer is such an omnipresent phenomena that you can find interesting problems to solve almost anywhere you look, right? Almost everything we do as human beings, as a society, involves heat transfer. Cooling of buildings, cooling of cell phones, the human body itself involves a lot of interesting heat transfer problems, a lot of therapy, cancer therapy, cryotherapy, etc. happens on the basis of heat transfer. I have a personal story to tell there. I had a little something in my back that was causing me some trouble, and the doctor said it was some growth on my bone inside. So the doctor said, okay, we will drill a little hole in your back and we'll basically zap it with some heat. As soon as he said heat, I said, interesting. So this is a true story. First of all, this little operation happened on my birthday. So I was lying down on the operating table, and just before they cut you open, they have to confirm for the last time that you are who you are supposed to be, right? So they asked me, what is your name? What is your date of birth? I told them my date of birth. It was the day of the operation. They said, and the doctor was a little funny. He said, now we are going to cut the birthday cake. And so what they did was that they drilled, they basically cut a small hole in the back, and then they took a electrode and they inserted it inside until the tip of the electrode was touching the bone where the problem was. And once it touched the bone is when they passed a bunch of current through the tip of the electrode, generated a bunch of heat, right, and basically zapped the little whatever that was causing trouble. And then he said, we have to wait for a little bit of time for the heat to propagate so that it completely zaps, and then he takes it out. And throughout all this time, I was still conscious, and I was thinking about all the concepts of heat transfer that apply to this problem. Okay, the point I'm trying to make is that problems related to heat transfer occur everywhere. Everywhere you look, there is an interesting heat transfer problem sitting there waiting for you to solve. So I want you to keep your eyes and minds open. I know as PhD students, you're interested in new ideas, new thoughts, new problem definitions. And so I'm telling you that heat transfer in particular is a very open, rich field in which to solve such problems. Anything and everything that is happening around us, energy, renewable energy, electric cars, climate change, etc., new materials, these are all things that involve heat transfer. So who knows, perhaps if you're looking for a good problem for your next project, who knows, that problem might be related to heat transfer. Okay. The other thing I would say is that the mathematical theory of heat transfer is also very rich. I have only scratched the very surface of this very rich mathematical field. There is a lot more mathematics that goes inside heat transfer theory. Everything that I talked in this class was mostly about thermal conduction, but there is also convective heat transfer and radiative heat transfer. And so perhaps if you are mathematically inclined, then looking at the mathematics of heat transfer theory is also one direction in which you can possibly go. Okay. Experimental measurements is also an interesting and important topic. I talked about this in the context of lithium-ion cells, but a lot of the principles that I have taught here are very universal. The concepts of repeatability, the idea of uncertainty, the importance of calibration, and in general, the importance of thinking about experiments and not necessarily doing. In most cases, the experiment itself, the act of taking a measurement, is not very difficult. You can always easily measure, right? However, you have to think much in advance about how you're going to do that measurement, how you're going to ensure that whatever you measure is indeed reliable and repeatable and has low uncertainty and all the other good stuff. Okay. We also, by the way, here, I will put here the lecture yesterday about technical communication. It was not a technical talk, but nevertheless it's extremely important, right? No matter what you do, you will be communicating your results through either written or oral means, and the quality of that communication ultimately determines what you get out of it, right? As I said, nobody is going to go to your lab and look at your setup. They will look at the picture of the setup that you show them in your presentation, and if that picture does not do justice to the hard work that you've done in your setup, then you are the one that loses. Yeah, so make sure that you do good work. I'm not prescribing a way to short circuit the importance of hard work, right? I'm not saying don't do anything, just make a good presentation. That's not the idea. What I'm saying is work hard in the lab, but then don't ignore the importance of being able to present it equally well. And remember, in both of my presentations yesterday, the one thing that I said again and again is the importance of practice. I'll say it one more time. Nobody is born with any innate skills as a presenter or as a writer. All of us get better and better at it with practice. The more you present, the more you write, the better you will get at it. So whenever there is an opportunity to present your work, raise your hand and be the first one to volunteer to give a presentation. Ask your advisor to get you involved more and more in the writing process. Write yourself, write every week. Every week, write 2 pages about your progress in research that week. That itself will help you generate more ideas. You know, when you write, you're actually thinking, your mind is thinking about the work. Your mind will think about the next steps, what went wrong, what might be done to fix what went wrong, what should I be doing next, how should I be fixing my problems, etc. These ideas come when your mind is engaged in the act of writing. So I would strongly recommend you all to think about technical communication almost as much as you think about the technical matter itself. Okay? Some of the things specifically with lithium-ion cells that we have looked at is the idea of internal thermal resistance of the cell and external resistance of the cell. So this is our internal and this is our external. Our internal has to do with the material of the cell, the thermal conductivity of the cell. And I've shown through simulations, experiments, etc., that usually the internal resistance of the cell is the dominant step. It's the rate limiting step. I can easily cool the cell down at the bottom, sorry, on the outside. And again, these are thermal resistances, folks, not electrical. I can easily make the external resistance as small as possible by blowing a bunch of air on it, liquid cooling, all that stuff. Usually it turns out that the internal resistance of the cell becomes a problem. And that is something that I don't have much control over necessarily. I can't blow more air over it and change the thermal conductivity of the cell. The thermal conductivity of the cell is a function of what is inside of it, how it is organized, and so on. And so there is a great need for innovations in materials science. There is a need to come up with better and better battery materials. And right now, that need is being driven by a search for better electrochemical materials. Materials which will charge and discharge faster, which will store more energy per kilogram, etc., etc. In my opinion, there is not sufficient work out there on understanding the thermal performance of such materials, right? That approach is completely justified. If you're looking for a better battery material, it needs to store energy, right? That should be the primary metric. But once you figured out that there is this material that can store energy very well, then secondarily, you must then worry about its capability to remove heat. So at some point in time, thermal engineers would have to start worrying about the thermal properties of all these new materials, these new battery chemistries that people are looking at. And I feel that a good collaboration between thermal engineers and material scientists can be very fruitful. So material scientists know a lot about the lithium intercalation and the materials that go inside of it and how lithium, diffuses and all that stuff. So, the focus of our class was on lithium ion batteries, but quite likely in the next 10 years, lithium ion technology will be overtaken by some other technology like sodium ion or potassium ion or whatever it be. It will bring its own set of challenges with it. And I want you as a thermal engineer to be ready for those challenges. Now that you know what the challenges in lithium ion cells are, quite likely the next generation technology will also offer some similar challenges and maybe some new challenges. I hope we all are ready to take up those challenges and to make contributions, for the next 20, 30, 40 years as your careers probably are going along. Okay? I have said at the very start of our class that lithium ion cells are a very multi-scale system. By the way, before I start talking about this, I do want to emphasize the importance of collaboration once again. None of us can do everything together. It is very important to extend a hand and create a connection with somebody else who has a synergistic expertise as you. And oftentimes it just boils down to making that initial connection, making that initial contact. So please never hesitate to go talk to somebody who you think can help you in your work. Trust me, people are always willing to listen. People are always welcoming new ideas, and somebody else, perhaps a material scientist, is also looking for a thermal engineer who can help them in their work, right? We all tend to work in our silos, unaware of each other, but if you make that initial contact, such collaborations are extremely fruitful. I know it can be a bit of a you can be a little hesitant to do that, to sort of introduce yourself out of the blue and all that, but do that, and trust me, these things lead to very good results. Within your institution, in other departments, if you go to a conference and meet other people, introduce yourself, tell them what you do and figure out what they do. And some of the connections I have made, in informal settings like dinners and lunches and so on, are the ones that have brought me a great deal of success in terms of research. Okay, so I would encourage you to do that. I have said that lithium ion cells are a multi-scale system, starting from atoms and molecules to components such as electrodes, anode and cathode, etc. to individual cells and to packs. You can perhaps find your niche anywhere in this scale, right? And this is a very large scale. Atoms and molecules perhaps at the scale of 10 to the power 9 meters, all the way. Large battery packs can be as large as 10 to the power 1 meter. Large battery packs, right? Depending on your training, your expertise and your interest, you can perhaps find an interesting problem to solve anywhere in this range. And the tools that you will use depends on the scale, right? Perhaps you're interested in using ANSYS as a simulation tool, in which case you will probably be somewhere here. You want to understand what happens to heat transfer in a large battery pack as it heats up and cools down. One important problem that we did not talk about in our class at all is that of fire. What happens when a battery pack catches fire? How does that fire spread? How do you extinguish that fire? And how do you prevent such fire in the first place? So one of my students, Dhananjay Mishra, I didn't get to talk about his research too much, but he spent a PhD looking at simulations of thermal runaway in battery packs. He now works for General Motors in Detroit, and the problem that he works on is actually very simple and almost silly. He says that General Motors is going to use tens of thousands of batteries in their electric cars. They're going to have to buy these batteries from somebody, and they're going to have to store them somewhere. So imagine a big warehouse, bigger than perhaps this building, where they have stored hundreds of thousands of cells ready to be used, integrated into their cars, right? What happens if there is a small fire in this warehouse? It's like storing this much petrol in one place, right? How do you prevent fires in a place like this? How do you place fire extinguishers in optimal locations? Imagine if I have this room full of batteries, what would be the right locations to place fire extinguishers? There are these things, bunch of water will come out and extinguish the fire. Is water even the right liquid for preventing battery fires, for managing battery fires? And suppose it is, then where do you place them? You see, do you place them at the top? Do you place them on the walls? Or do you place them on the ceilings? Those are the kinds of questions, very practical questions, that he's trying to answer. He says, they move their battery packs using forklifts. You know what a forklift is, right? Suppose the forklift operator is negligent and he or she runs the forklift into a battery pack, into a bunch of battery packs, and they fall down on the ground. The very act of the battery falling down on the ground may rupture it and cause a thermal runaway event. So you can imagine there are all kinds of practical problems that storage and use of battery packs can cause. Can you come up with some interesting question that you want to answer in that regime? One problem that one of my students and I are just beginning to work on is the problem of cargo transportation of lithium-ion cells. So imagine if you have to transport a large number of cells and you put them in the cargo hold of a plane, then that can be very dangerous, right? Because any small malfunction there can cause a fire, and then you have to figure out how to fight that fire. All cargo holds in a plane are equipped with some fire extinguishers that are designed to start as soon as there is a fire. But an open question is, are those fire extinguishers appropriate for battery fires or not? And if they are not, then what do you do about it? You cannot possibly go to every plane and change the fire extinguishing mechanism in all planes, right? How do you use the system that you already have in the best possible manner in order to do what you want to do, right? Those are the kinds of questions that we are trying to answer right now. Question?
So the last time when you were given the seminar, you were discussing about that simulation in which you have simulated thermal and everything.
Yes, correct. Yes, absolutely. I had given a virtual seminar at IT Ropert 3 years ago, 2 years ago, something like that, in which I had discussed that aspect of the work in detail. I didn't talk about this in this short course, mainly because I didn't want to repeat. Anything else? Okay, cool. Yes. Yes. Well, the parameters we study are, firstly, if this is a cargo hold and I have pallets of batteries, then how far should these pallets be placed? What should be the gap between these pallets so that if one of the pallets catches fire, the fire does not spread to the next pallet? Strictly speaking, if I keep my pallets far enough, then the fire will not jump from one to the other. But then what that will mean is that I will only be sending 2 pallets in a plane when I could have sent 10. You know what I'm saying? But if I keep them too close to each other, then the fire is going to spread very easily. So we do simulations in which we try to understand what is the minimum distance between pallets in order to prevent such fires. Particularly in the case of cargo planes, one interesting challenge is that the temperature up there is very different from the temperature on the ground. Typically it's very cold up there at the heights that the plane travels at, and the pressure is also very low. The cargo hold is not pressurized. So the batteries are seeing very low pressure ambient. And that's a problem because inside the battery there is very high pressure. Now outside if the pressure is low, then there is a lot of stress on the walls of the batteries. And any little thing can cause rupture. So one question is it acceptable to transport batteries in a low pressure cabin, in a low pressure cargo compartment, or do you need to transport it, do you need to pressurize the cargo compartment or not? Does that make sense? Cool. So I think fire is an important thing that we really didn't talk about too much in our class here, but nevertheless is a very important topic. It's also a very practical question. If there is a battery fire, if an electric car catches fire on the highway and the firefighters come, they need to know how do they handle this fire. Do they pour sand on it? Do they pour water on it or what? There have been accidents in the US where an electric car, hits something, catches fire, the firefighters come, they extinguish the fire and they go away, and 2 hours later it catches fire again somehow. There is a term for it, reignition or something like that, and people don't quite know why that happens and what you can do to prevent reignition from happening. There are all kinds of open questions related to battery fires. Personally, I am very interested and excited about the theoretical ramifications of thermal runaway. The idea of thermal instability. Like I have said, instability is a phenomena which is very well studied in mechanical vibrations, in fluid mechanics and so on. We know when a mechanical system can become unstable, right? Resonant frequency and all those concepts. We know when a fluid system can become unstable and lead to turbulence and so on, right? The understanding of instability in the context of heat transfer is not as well known, and therefore I think there remains work to be done in the area of instability in the context of lithium ion cells. So can we come up with better strategies to predict thermal runaway in advance is the main motivation driving that theoretical work. You see, if I have a battery pack and if it starts undergoing thermal runaway, then it is already too late for me to do anything about it, because those chemical reactions have already started. They are going to generate heat. Even if I somehow start cooling them, that heat will cause the next set of reactions to occur, and very soon the entire battery pack will catch fire. It's like having a room full of some volatile gas, like cooking gas. If I light a matchstick and if that explosion starts, it is already too late for me to do something about it, right? I need to prevent thermal runaway much ahead in advance and not wait for the event to actually have started already. So proactive prediction and prevention of thermal runaway, I think is a very important topic. Prediction and prevention of thermal runaway, I think is a very important topic, both from an applied point of view. If I give you a battery pack, can you run some experiments or some simulations to predict the limits up to which you can take this battery pack before it becomes dangerous, right? And also from a theoretical point of view, forget about an actual battery pack. Suppose you have a thermal system and you want to do some applied mathematics, then that also is a very rich field in which to do some good work. Can you come up with the next non-dimensional number that will predict the occurrence of thermal runaway and so on and so forth? So I feel, and I'm having seen this, I'm very passionate about this. I feel that there are some very interesting theoretical problems as well as applied problems for us to solve in this field. Okay, any questions or comments yet? The other thing I would like to say is that heat transfer in lithium ion cells, but also in general, is usually very highly coupled with some other phenomena. Usually heat transfer does not occur only on its own. In the case of lithium ion batteries, the other physical process that happens along with heat transfer is electrochemistry. We learned a great deal from Professor Agrawal's 2 seminars on electrochemical modeling of lithium ion cells, and that is important because the heat generated in a cell, which makes us worry about all the other things that we have worried about, happens because of electrochemical reactions, right? So this in some sense is the root of the problem. If I want to truly understand heat transfer, I really need to start learning electrochemistry. My students and I have learned a little bit of electrochemistry as we go. Of course, there are other experts who have built careers out of electrochemistry, and sometimes we talk to them and we get their help. One way or the other, we never say, oh, I am a heat transfer engineer, don't ask me about electrochemistry, right? That's not the right approach. The right approach is to say, okay, I'm a heat transfer engineer, the system I'm studying involves electrochemistry, I need to teach myself enough electrochemistry, or I need to shake hands with someone who knows enough electrochemistry in order to solve the problems that I'm wanting to solve. So my other advice to all of you is to be open to new fields and new areas in your careers. In the 30 or 40 years of careers ahead of all of you, it is quite likely that you will not be doing the same thing that you're doing today. It is quite likely that you will perhaps not even be in the same department that you are in today. It is possible that 20 years later you will not even be doing engineering at all. You might be doing something entirely different, right? There's only a few of us, myself included, who stick to something that they learned 25 years ago, okay? So 25 plus years ago, I was sitting in a room, taking a class in thermodynamics, and something inside me said, wow, this is so cool. And I have the privilege of being able to do the same thing even 25 years later, okay? Somebody might call it very boring, and I can understand that, all right? To each their own. Perhaps you will stick to what you're doing and do it for a long time, but quite likely, in the majority of cases, you will be looking at other things, other systems in the near future, in the next 5 years, 10 years, 15 years. And the one very important thing is to be a lifelong learner. Be open to stepping outside your comfort zone. We all have a comfort zone. I know heat transfer very well, and I'm very comfortable solving heat transfer problems, right? It takes an effort to step out of your comfort box and start learning about new areas, new fields. And it takes time, it takes a lot of patience, but it is something that I think is extremely important to do, right? So please be open to being a lifelong learner. You never know what direction your next opportunities will come from. You have to be open to such new opportunities, and don't ever be a thermal engineer forever. And this is especially true if you're going to go and work in the industry. If you're going to finish your master's or your PhD and go work in a company, then you will find there that nobody is a mechanical engineer, nobody is a thermal engineer. Everybody, by definition, engineers are problem solvers. Whether those problems come from your area of expertise or other areas of expertise, you're responsible for solving those problems. So go figure out how to solve problems. And in some sense, doing a master's or a PhD is teaching you, exposing you to difficult problems and challenging you to solve those difficult problems. Once you have solved some difficult problems successfully in a PhD or a master's, I feel that you are now ready to take up any other problem in the world and solve it confidently. The point I'm trying to make is that the problems in the future may or may not come from the same area in which you are working. Okay. I also want to say that there are a number of open problems at the intersection between heat transfer and electrochemistry. For the precise reason that people are not comfortable stepping outside their zones, heat transfer people have done a lot of heat transfer analysis of cells. Electrochemists have done a lot of good electrochemical analysis of cells. What is lacking is somebody at the intersection between heat transfer and electrochemistry to be able to integrate the two in one shot. So thermal electrochemical modeling, thermal electrochemical modeling is a topic of a lot of current interest right now. Remember, for example, the heat transfer modeling that we did, we said k d2t by dx2 plus q of t is equal to rho cp dt over dt. And as an approximation, we simply said q of t is equal to beta times t. Q of t is the heat generation that occurs because of electrochemical reactions. And I made a very gross simplification that all the electrochemistry that is happening is being bunched together into this parameter beta. And I'm assuming I know the value of beta, right? That may be a reasonable way to start, but certainly requires more sophistication. This beta comes from electrochemistry. On the other hand, when electrochemists solve these problems, like the equations that Dr. Agrawal had presented, I forget the exact formulation of those equations, but roughly speaking, Fick's law, yep. Del by del x of d dc dx plus blah 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 equals something else. He wrote all those equations assuming that the temperature is the same everywhere. He assumed isothermal conditions, because of which his diffusion constant was a constant. It was not a function of temperature.
Because when multi-deriving, it is not a constant. We can keep it as a function of temperature also.
We can do that, but that significantly complicates the calculations, right? So the point I'm trying to make is that the thermal model, strictly speaking, does not stand by itself. It is dependent on the electrochemical model. And similarly, the electrochemical model itself is dependent on the thermal model. You need to solve the thermal field to be able to know your D, so that you can solve the concentration field. And only after you can solve the concentration field will you know how much heat is being generated, which goes as an input into this equation. So it's sort of like a chicken and an egg problem. There cannot be an egg without the chicken, but then there can also not be a chicken without the egg, right? So which came first? My approach is they both should come together.
When we couple it is like that.
Exactly.
The output of electrochemical model will be the input for
And vice versa.
and
This loop will keep going on and on. Absolutely. There is a need for us to come up with better integration between thermal models and electrochemical models at the scale of atoms and molecules, at the scale of anodes and cathodes, at the scale of individual cells, and also at the scale of large battery packs. In this class, our discussion of stuff that happens at the scale of atoms and molecules was very limited. Right here, I only very briefly discussed molecular dynamics simulations. At the scale of atoms and molecules, MD simulations is a very commonly used tool for both heat transfer and electrochemistry. So if you would like, I mean, it's not trivial. It's not something that you can learn in a day or so. It does take a significant amount of effort and commitment. But if you can teach yourself molecular dynamics simulations, then there is really not a lot of people working on MD simulations for lithium ion cells. There's an army of people doing MD simulations for all kinds of things under the sun, right? But can you learn enough MD simulations and create a niche for yourself by applying MD simulations for solving some interesting lithium ion cells related problems? Nothing that I'm talking about here is trivial, right? I'm not giving you a key that go and tomorrow you will have enough ideas to do your PhD. Each of the thoughts that I'm trying to ignite in you will take some effort, and it's quite possible that you think about something for a while and then decide, look, this is simply not feasible for me. I am simply trying to start a thought process in you all, a conscious thought process to think about what are the right things for me to work on. And trust me, believe me, having done a PhD myself and having seen several PhD students in my lab, this is the most difficult part of doing a PhD or a master's, right? Identifying the problem statement, what it is that you want to do. Once the problem statement has been identified well, then solving that problem itself is not that difficult, right? You all have taken so many classes, will take several classes that teach you the tools, right? You can take a semester long class in MD simulations. It will teach you the tools to solve problems. It will not tell you what problem to solve, right? That is up to you. That is for you to read the literature, read review papers, good quality review papers, and get an understanding of what are good problems to solve in this field using the tools that I have learned or using the tools that I can learn. You may not know MD simulations today, but if you find that I really want to do MD simulations for lithium ion cells, next semester you can sign up for a class on molecular dynamics simulations, either here at Roped in person or online, right? These days the possibilities are limitless. You teach yourself MD simulations by whichever way you need to, and you are then ready to solve problems related to lithium ion cells. I am myself not an expert in this field, but I feel that this is a very good topic for you, for anyone to make some good fundamental contributions in. And the good thing about it is that as with an expertise in MD simulations, you're ready to solve all kinds of problems in the world, not just lithium ion cells, but who knows what in the future, solar cells, energy conversion, God knows what in the future. Okay, any questions or comments so far? All right, what else do I want to say here? Let's see, let's go back to the original, the first slide. Let me say a few things about experimental measurements as well. Everything that I've taught here applies very generally, right? So experimental measurements is something that many of you will probably be doing for your PhDs. It may not be measurement of temperature, it may be measurement of something else. But some of the principles that I have taught in this class in the context of temperature measurement for lithium ion cells applies in a very general framework. Anytime that you want to measure something, you have to think very carefully about how you're going to measure it. Please don't jump into the fire right away. Think about what you're going to do, how you're going to do, what is the best way of doing it, how do you ensure that you have confidence in your measurements and so on. And only when you think you're ready is when you are ready to jump in. Okay? Create a team around yourself. Have somebody, some trusted person you can talk to and bounce your ideas around. Talk to your advisor certainly, but also somebody else, maybe a lab mate or something like that, who can help you refine some of these ideas, right? Experimental measurements are beautiful. Once you have a good system in which you are able to take good measurements, it looks very good to get experimental data, but it does take quite a lot of effort to get there. You have to worry about what equipment you will need, what consumables you will need, and of course you may have to order some and it takes time for it to come around. And during that waiting time, I hope you're thinking that, look, when my instrument is here, what am I going to do with it? What will my strategy for measurements look like? What will I measure? How will I measure? How much will I measure? How many times will I measure? How will I analyze all that data? What will I do with all that data? What are some good questions to ask with that experimental setup? For example, the immersion cooling setup, Swapnil's immersion cooling setup that we talked about, had a bunch of cells immersed in a coolant with a bunch of temperature sensors, pressure transducers, and the ability to pump fluid back and forth through the system, right? Having created a simple system, well, I wouldn't call it a simple, but having done the hard work to create this system, now is the time to think creatively about all the cool things that you can do with this, right? Brainstorming is extremely important. What kinds of questions can you ask from this system? Question number 1, can immersion cooling prevent thermal runaway? That's probably a question that I want to answer at the very end, because cells may explode and I will not have my setup again, right? So only after I have asked a bunch of other questions, published 2 or 3 papers, will I commit to the risk that things might blow up. Yeah, and of course your personal safety and the safety of the lab, etc. is important. So you need to think about all that. One thing that we had learned was that this cell gets very cool, but this cell remains hot because of the direction in which the coolant goes. A very simple way of solving that problem is to periodically change the direction of the flow of the coolant. So this pump that you have outside sort of becomes a two-way pump. I can pump in this direction, and when I want, I can start pumping in the opposite direction to sort of make it equal for all cells. If I do that, how frequently should I change the direction of the flow is an interesting question. You see, I'm a firm believer that once you start thinking about a system very hard, you stare at that system enough, you can and you will come up with all kinds of interesting questions to ask. Yes? Hmm.
Maybe will flow there will be some point that the temperature gradients will create inside the stack.
Yes, absolutely.
And to remove, we can use some different type of configurations into it.
Yes, I want you to be creative. I want you to be, the possibilities are endless, right? Who is stopping you from creating multiple inlets and multiple outlets, right? Oops, I don't want you to do that. What if I have multiple inlets and outlets? So this is an inlet, this is an outlet, this is an inlet or outlet or whatever have you. What are the best places to place, what are the best locations in your rig to place these inlets and outlets? How will you answer that question? One way to answer that question is to place a large number of inlets and outlets and plug them up. Run experiments in which you open this one, close this, then close this, open this, close that, open that, etc., etc. You can play a beautiful jigsaw game, right? Once this experimental setup is there. So once you worked hard to set something up, don't let it go easily, right? It's like, I don't know what it's like, but once you have caught this in your, once this is in your hands, look at it this way, look at it that way, right? Don't let go of it until you have exhausted all possible questions that you can think of. Okay? Any other interesting things that we can do here? Thermal runaway we said, directionality of flow we said.
spacing between the cells.
Yes.
Yes. Approximately 1 mm.
Yeah, something of that order.
Because I haven't seen it
Hmm.
with myself. They are using a paste,
Hmm.
one paste type of thing, to just stick it, and that to approximately 1 mm.
Right.
And in between that, to provide each and every type of cooling.
Yes.
Like we are sitting in that, we will have space and all.
Yes.
The visual impression that it is having that space. But if you draw on the cells, it will we will just like coinciding or touching.
Almost, yes. Almost coinciding,
In
yes.
that scenario, if we try to do all these things, what?
Good question. I don't know the answer to that. How does this fairly viscous fluid penetrate into the nooks and crannies of the battery pack? I would like to go back and ask the question of why the cell to cell gap is only 1 mm in the first place. Can we make it 2 mm? Maybe the original choice was arbitrary. Maybe they said, I just want to get them very close, so let's make it 1 mm. Maybe if you keep them 2 mm apart, it really won't hurt the spacing, the size too much. But the change in gap from 1 mm to 2 mm, from a heat transfer point of view, can significantly improve heat removal. Maybe.
I ask a similar thing.
Yes.
When we think about the small module,
Hmm.
then this thing is come. But when we think about a whole battery pack,
Sure.
if we increase the 1 mm gap,
It adds up.
It will create a huge difference between the whole total battery capacity.
Sure,
Because
absolutely.
the one line can be removed.
Sure. So you have to come up with what is the optimal spacing there. Maybe not 2 mm, but maybe 1.5 mm will give you a reasonable compromise between the two. I don't know the answer to it. I'm forcing you to ask questions. It's up to you to find the answers. And the answer to this question can probably come from a combined approach between experiments and simulations. It's very difficult to run these measurements at 1 mm, 1.5 mm, 2 mm, etc. Right? Changing the size of the gap between cells is not trivial. But you can, just like Swapnil did, create a numerical simulation in which it is much easier to change the gap, run a new simulation and see what your simulations will predict. When you do have numerical simulations, I think it is very important to have validation. Anybody and their uncle can create a numerical simulation and get some results out and show it to the audience, right? How do you believe those results? That validation, I think, is extremely important. In order to show a good, tight PhD dissertation that people can believe in, it is important to take results from numerical simulations and compare them with experimental data. That experimental data doesn't have to be yours. It could possibly be somebody else's experimental data reported in the past, right? That is quite acceptable. In fact, when we write a manuscript, a paper, it looks very good when you're comparing your results with results from somebody else. When the two are in good agreement with each other is when there is good confidence in those measurements. Okay? So we are at 12:30. I will stop here. I hope the Gyan course was helpful and useful to you all. Please stay in touch. You have my email address. Even several years later, I would be interested in learning about where you are, how you got there, are you still working on batteries, and whether what you learned here in the Gyan course in some little manner helped you in your careers. All right. So with that, I'll thank you all. It's been a pleasure. Thank you, Himanshu ji and Kulbhushan ji, for all the facilitation. As you can see, he's doing double duty. He's trying to learn and at the same time